Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication systems. In the previous module, what we have seen is we have seen the Alamouti transmission scheme for a MIMO wireless, or more specifically for a 1x2 MISO wireless communication system. What we are going to start with in this module is the bit error rate performance of an Alamouti coded MISO wireless system. So, let us look at the bit error rate performance of this Alamouti coded system. As we already seen, Alamouti is an orthogonal space-time block code. So, the bit error rate of this Alamouti coded system. Now, let us look at the SNR. The SNR of this Alamouti coded system, the SNR is norm h square p divided by 2 sigma square. Remember, we said there is a loss of half compared to maximal ratio combining. So, norm h bar square times half into p over sigma square, or half times SNR, or half times p over sigma square, which is equal to norm h bar square half times the SNR. So, basically it has MRC is identical to MRC with half the SNR, half the transmit SNR p over sigma square. There is this factor of half. Therefore, the bit error rate is similar to that of MRC with 2 antennas. Remember, the number of antennas in this MISO system, Alamouti coded MISO system, is 1x2. Therefore, the number of antennas is 2, or L is equal to 2. So, therefore, it is identical to the performance of an MRC system with L equal to 2 antennas, but half the transmit SNR. Therefore, the bit error rate at high SNR equals twice L minus 1 choose L 1 over 2 times half SNR, because we said the transmit SNR there is a factor of half raised to the power of L. The other thing is we have to substitute L is equal to 2. So, therefore, it is 3 choose 2 1 over SNR raised to the power of 2, which is basically 3 divided by SNR square. So, the bit error rate of this Alamouti coded wireless system, it's interestingly we are able to derive an expression for the bit error rate of this Alamouti coded wireless system, and that is 3 divided by SNR square. So, this is the bit error rate of Alamouti coded the bit error rate of our Alamouti coded wireless system is 3 divided by SNR square. This is the average bit error rate, mind you, averaged over the distribution of the fading channel coefficients. We are assuming the fading channel coefficients H1, H2 to be IID relay with average power 1. That is the standard assumption when we derive the bit error rate of this system with maximal ratio combining. All right. So, remember, this is the average bit error rate. This is average bit error rate under the assumption H1, H2 are IID relay average power equal to with average power equals 1. This is the assumption that we are using here. Okay. All right. Now, let us look at some examples of this Alamouti coded wireless communication system. To understand this better, let us look at some simple examples. Okay. So, let us start with example of Alamouti processing. Example of Alamouti processing. Let us consider a simple system y equals 2 plus j 1 minus 2j times x1 x2 plus W, correct. So, basically this is my channel coefficient H1, this is my channel coefficient H2, H1 is equal to 2 plus J, H2 is equal to 1 minus 2J, this is my 1 cross 2 MISO, this is my 1 cross 2 MISO system. There are two channel coefficients H1, H2, H1 is equal to 2 plus J, H2 is equal to 1 minus 2J. In the first transmit instant, in the first transmit period, we are transmitting, what are we transmitting? We are transmitting x1 from the first transmit antenna and x2 from the second transmit antenna, correct. In the first transmit period, we are transmitting x1 from the first transmit antenna, x2 from the second transmit antenna. So, I have y1 equals 2 plus j 1 minus 2j the row vector times x1 x2 the column vector plus w1. During the second transmit instant, during second transmit instant, what do we have? We are transmitting minus x2 conjugate from the first transmit antenna and x1 conjugate from the second transmit antenna, remember that, okay. It is the same symbols x1 and x2, but from the first transmit antenna we are transmitting minus x2 conjugate, from the second transmit antenna we are transmitting x1 conjugate. Therefore, we have y2 equals 2 plus j 1 minus 2j minus x2 conjugate x1 conjugate plus w2, which is equal to 2 plus j times x2 conjugate minus 2 plus j times x2 conjugate plus 1 minus 2j times x1 conjugate plus w2. Let me rewrite that over here. I have y2 equals minus 2 plus j times x2 conjugate times x2 conjugate plus 1 minus 2j times x1 conjugate plus w1, which is equal to, now if I take y2 conjugate, I have y2 conjugate equals minus 2 minus j into x2 plus conjugate of 1 minus 2j, which is 1 plus 2j into x1 plus, or rather w, this should be w2, this should be w2, this should be w2 conjugate, which is equal to, now if I write this as 1 plus 2j and I have here minus 2 plus j times x1 x2 plus w2 conjugate. And previously what did I have? Previously I had y1 equals, I had 2 plus j 1 minus 2j times x1 x2 plus w1. Now, when I combine these both, I have y1 y2 conjugate is equal to 2 plus j 1 minus 2j 1 plus 2j minus 2 plus j times x1 x2 w1 w2 conjugate, and this is my vector y bar, this is my 2 cross 2 matrix, this is my vector x bar, this is my additive Gaussian noise vector w bar, and these are my columns C1 bar, C2 bar. Now, let us look at C1 bar and C2 bar. C1 bar equals, what is C1 bar equals, that is 2 plus j 1 plus 2 j C2 bar equals 1 minus 2 j minus 2 plus j, that is the second column of the matrix. Now, therefore, C1 bar Hermitian C2 bar equals, well, transpose, Hermitian means transpose and take the conjugate 2 minus j 1 minus 2 j times 1 minus 2 j minus 2 plus j, which you can clearly see this is 2 minus j into 1 minus 2 j plus 1 minus 2 j into minus of 2 minus j, which is equal to 2 minus j into 1 minus 2 j minus 1 minus 2 j into 2 minus j, which is equal to 0. So, now in this example we are seeing that we have constructed this Alamouti matrix, we have extracted these two columns C1 bar, C2 bar, and what we are seeing is that C1 bar Hermitian C2 bar is 0. That is why we said Alamouti is an orthogonal space-time block code. This orthogonality of the columns at the receiver in this Alamouti matrix makes the decoding operation very easy. Notably, it is a simple correlation operation and not a matrix inversion, correct. So, it is an orthogonal space-time block code. Therefore, to decode x1, we perform C1 bar Hermitian by norm C1 bar into y bar, which is equal to, well, now let us extract norm C1 bar. What is norm C1 bar? Remember, C1 bar equals, well, 2 plus j 1 plus 2 j. Therefore, norm C1 bar equals square root of magnitude 2 plus j square plus magnitude 1 plus 2 j square, which is equal to under root 4 plus 1 plus 1 plus 4, which is equal to square root of 10. So, norm C1 bar is equal to square root of 10. Therefore, we perform C1 bar Hermitian divided by norm C1 bar times y bar to extract x1, that is square root of 1 over square root of 10 C1 bar, which is 2 minus j 1 minus 2 j times y bar, which is y1 y2 conjugate, which is equal to 1 over square root of 10 2 minus j into y1 plus 1 over square root of 10 1 minus 2 j into y2 conjugate. And what does this yields us? This yields us, or this helps us extract x1. Alright. So, what we are doing is we are beamforming along C1 bar Hermitian divided by norm C1 bar times y bar, which is the vector in the Alamouti coded system, and that helps us extract the symbol x1. Similarly, to extract the symbol x2, we perform C2 bar Hermitian divided by norm C2 bar times y bar, and also you can see that norm C2 bar is also equal to norm C1 bar is equal to square root of 10. Therefore, to extract x2, I perform 1 over square root of 10 C2 bar Hermitian, that is 1 plus 2 j minus 2 minus j times y bar, which is y1 y2 conjugate, and this is equal to 1 over square root of 10 1 plus 2j into y1 minus 2 plus j over square root of 10 into y2 conjugate, and this helps us extract the symbol x2. So, beamforming along C2 bar Hermitian divided by norm C2 bar, that helps us extract the corresponding symbol x2. Now, let us look at a simple example to evaluate the bit error rate performance of this Alamouti system. So, let us evaluate the bit error rate. Example for BER bit error rate of the Alamouti coded system. And bit error rate of Alamouti coded system, for instance, let us look at this simple example. Consider a 1 cross 2 MISO system. Consider a 1 cross 2 MISO system with Alamouti coded 1 cross 2 MISO system with Alamouti coded transmission, and what we want to do is we want to consider an SNR of 25 dB, and we want to ask the question what is the bit error rate. So, what we are doing is we are looking at a simple example for the bit error rate evaluation in an Alamouti coded 1 cross 2 MISO system. We have an SNR of 25 dB. We want to ask what is the average bit error rate at this SNR. We have already seen the average bit error rate of Alamouti equals 3 divided by SNR square. Now, we are given SNR dB, that is 10 log 10 SNR equals 25, which means SNR equals 10 to the power of 2.5. Therefore, the average bit error rate is 3 divided by SNR square, which is 3 divided by 10 raised to 2.5 square, which is 3 divided by 10 to the power of 5, which is basically 3 into 10 to the power of minus 5. So, the average bit error rate, so this is average bit error rate of Alamouti at SNR equals 25 dB. So, this is a simple example to illustrate the average bit error rate of an Alamouti coded 1 cross 2 MISO system at SNR 25 dB. We have seen that is 3 into 10 to the power of minus 5, that is the bit error rate. All right. So, these examples and the theory before that comprehensively illustrate the analysis, the theory, the scheme, the analysis, the transmission, the decoding, and also the bit error rate performance of this Alamouti coded system. And Alamouti is a very important transmission scheme, or considered a key step, a key milestone in the progress or in the development of wireless communication system, because of its elegance, because of its simplicity, because of its convenience. Remember, we said Alamouti coded system, it is an orthogonal space-time block code. It has two aspects. One, it does not need the channel state information at the transmitter. Two, the decoding at the receiver is very simple because of the orthogonal structure of Alamouti, and therefore, these two techniques combined make Alamouti a scheme which is very convenient and very convenient for implementation in a practical wireless communication system. Hence, it has been included in 3G and 4G wireless standards. And what we have seen is, we have seen the theory behind the Alamouti scheme, and we have also seen its performance in terms of the bit error. All right. So, we will conclude this module here and explore other aspects of MIMO in subsequent modules. Thank you very much.